The K-Hypertube High-Speed Vacuum Train, also known simply as the Hypertube, represents South Korea's bold vision for the future of ultra-high-speed ground transportation, a system that merges magnetic levitation with near-vacuum tube technology to achieve speeds faster than even commercial airplanes. Developed under the leadership of the Korea Railroad Research Institute (KRRI) with the support of the South Korean government, this project aims to transform how people travel between cities by cutting travel time from hours to mere minutes. The Hypertube concept operates on the principle of drastically reducing air resistance by placing a magnetically levitated train inside a sealed tube maintained at an extremely low air pressure, approximately 1/1000th of normal atmospheric conditions. This near-vacuum environment allows the train to glide through the tube almost frictionlessly, propelled by electromagnetic forces. The targeted top speed is around 1,200 km per hour, nearly the speed of sound, and once operational, a journey from Seoul to Busan, which currently takes almost 2 hours even on the country's KTX high-speed trains, could be completed in only 15 to 20 minutes. The Hypertube's design philosophy rests on three essential pillars: efficiency, sustainability, and safety. Efficiency is achieved through the combination of advanced magnetic levitation and linear motor propulsion systems, eliminating physical contact between train and track and minimizing mechanical wear. The project's engineers are exploring superconducting electromagnets that can maintain strong magnetic fields with minimal energy loss, drastically improving performance and reducing maintenance costs. Sustainability is another cornerstone, since the train will have no direct carbon emissions and could be powered through renewable energy sources, such as solar panels installed along the length of the vacuum tube or wind energy integrated into the national grid. It offers a green alternative to both air and conventional rail travel. Safety, perhaps the most complex component, is being addressed through redundant vacuum maintenance systems, sealed capsule designs, and emergency decompression protocols designed to protect passengers even in the rare event of system failure or tube damage. South Korea's ambition for the Hypertube is not just technological, it is symbolic of the nation's determination to lead in next-generation transportation. In the global race for hyperspeed travel, concepts such as Elon Musk's Hyperloop in the United States or similar efforts in China and Europe have drawn international attention. However, South Korea's approach is distinguished by its disciplined, step-by-step research methodology. The KRRI began experimenting with small-scale prototypes as early as 2017, achieving a remarkable 1,019 km per hour in a 1/17th scale vacuum test environment by 2020. These early trials proved the physical feasibility of achieving near supersonic speeds within a low-pressure system and gave engineers valuable data on drag, levitation stability, and heat buildup at extreme velocities. Now, with government funding of approximately 12.7 billion won, roughly $9 million United States dollars, allocated between 2025 and 2027, South Korea is transitioning from laboratory testing to the development of full-scale components, including long-distance vacuum tube sections, advanced maglev propulsion systems, and automated control units. If successful, the K-Hypertube could redefine transportation economics and regional dynamics within Korea. At such extraordinary speeds, national boundaries within the peninsula could effectively blur, turning distant cities into accessible suburbs and allowing people to live and work in different parts of the country without long commutes. For example, someone living in Busan could work in Seoul and return home the same evening in less time than it currently takes to cross a congested city by car. This kind of connectivity has the potential to decentralize population concentration in Seoul, promote balanced regional growth, and relieve infrastructure pressure on existing transport systems. The South Korean government sees this as part of a broader strategy to enhance regional competitiveness, improve quality of life, and position the country as a global pioneer in sustainable transportation technology. However, transforming this vision into reality poses formidable challenges. Maintaining a low-pressure environment over hundreds of kilometers is an engineering feat that requires perfect sealing, constant vacuum monitoring, and advanced pumping systems capable of counteracting tiny leaks that could otherwise destabilize pressure equilibrium. Structural integrity is another concern. The tube must withstand not only external atmospheric pressure but also environmental factors like temperature variations, ground movement, and even seismic activity. Engineers must also address aerodynamic phenomena unique to near-vacuum environments, such as the Kantrowitz limit, which occurs when residual air is compressed in front of the vehicle, potentially creating resistance and shock waves that could destabilize the train at high speeds. Additionally, passenger comfort presents an entirely new set of challenges. Acceleration and deceleration forces must be kept within human tolerance levels, vibration and noise must be minimized, and emergency escape systems must be designed for a fully sealed vacuum tube environment. Another critical issue lies in energy demand and efficiency. Accelerating a large train to supersonic speeds requires immense power, and maintaining a vacuum over long distances consumes additional energy. The KRRI's current studies are therefore focused on optimizing the train's aerodynamic profile, using lightweight materials such as carbon fiber composites and titanium alloys, and incorporating regenerative braking systems that can recapture energy during deceleration. Advanced AI-based control systems will monitor every component, from pressure valves to maglev coils, ensuring stability and preventing cascading failures. These technologies, while costly to develop, could ultimately reduce operational expenses and make the hypertube commercially viable. The K-Hypertube also raises important economic and social questions. Constructing the network will require vast investments in infrastructure, including elevated guideways, vacuum pumps, power substations, and specialized maintenance facilities. Land acquisition and environmental assessments will add to both the complexity and cost. While the current R&D budget is relatively modest, building a full-scale operational route could require tens of billions of dollars. The Korean government is expected to engage private sector partners, universities, and international investors to share the burden of development. Critics argue that such enormous costs may not be justified unless the system can achieve significant ridership and compete directly with short-haul flights. Proponents, however, believe that once proven, the hypertube could revolutionize global transportation in the same way that the jet engine transformed aviation in the 20th century. In addition to domestic benefits, the hypertube could become a major export technology for South Korea. The country already has a strong reputation for high-speed rail, as demonstrated by its KTX and SRT networks, and has exported rail technology to countries such as Turkey and Indonesia. A successful hypertube prototype could allow South Korea to license its technology abroad. Partnering with other nations seeking fast, efficient, and environmentally sustainable transport solutions. The government has hinted at future collaboration opportunities with ASEAN countries and even potential integration with intercontinental projects connecting to Japan or China through undersea tunnels, although these remain distant possibilities. One fascinating aspect of the hypertube is its potential synergy with artificial intelligence and smart infrastructure. Each train capsule could be equipped with autonomous navigation systems capable of communicating with the tube's control grid in real time, ensuring precise synchronization between vehicles traveling at near supersonic speeds. The infrastructure could also use predictive maintenance algorithms to detect wear, temperature changes, or pressure anomalies long before they pose safety risks. Integrating these technologies could make the hypertube not only one of the fastest but also one of the safest and most reliable transportation systems ever built. Despite the excitement surrounding this innovation, scientists remain cautious. Many unknowns remain unresolved. How will human bodies react to sustained near-supersonic travel in an enclosed tube? How will emergency evacuation be handled in a sealed environment without compromising the vacuum? What will be the psychological impact on passengers traveling at such speeds without windows or visible references to the outside world? Engineers are exploring creative solutions, such as virtual reality displays to simulate windows and dynamic lighting to reduce disorientation. Nonetheless, extensive human factor testing will be required before commercial operation can begin. As of 2025, the project is in the advanced research phase, with a goal to build a mid-scale demonstration line by 2027. The next major milestone will be to construct a test track several kilometers long to validate propulsion, levitation, and vacuum maintenance under realistic conditions. If these tests succeed, South Korea could move toward full-scale prototype operations in the early 2030s. Although it may take decades before a nationwide hypertube network becomes reality, the technology's promise already symbolizes the country's ambition to leap beyond the limits of traditional transportation. Ultimately, the K-Hypertube represents more than just a new train, It is a glimpse into the next era of human mobility. It challenges the boundaries between science fiction and reality, blending cutting-edge physics, materials science, and engineering with a vision of sustainability and progress. In a world increasingly defined by the need for speed, efficiency, and environmental responsibility, South Korea's Hypertube stands as a beacon of what is possible when imagination meets determination. Whether it eventually succeeds or not, its development will undoubtedly inspire future generations of engineers, scientists, and dreamers to continue pushing the limits of what transportation can be: fast, clean, and astonishingly futuristic.